Here you can see an assembly that represents the turning mechanism of the Wankel rotary engine, which consists of just a few parts and a subassembly: the housing, the eccentric shaft, the rotor subassembly, and a gear. When I rotate the triangular rotor block, you can see where the stages of intake, compression, ignition, and exhaust would occur. You might also notice that for every full rotation of the rotor, the eccentric shaft makes 3 full rotations. This allows for higher revolutions per minute from a smaller amount of work. I'll show you how I put this assembly together. First, I'll go over the initial sketch for creating the triangular block and a simple circular pattern method you might find on the CSWE exam. I'll move the rollback bar to below the first extrude, which makes the general shape of the part, and open the sketch. At first glance, this sketch might look pretty complicated. To break it down, it consists of 2 construction triangles, one pointing up and one pointing down. The size of the part is driven by the lengths of the sides of these triangles. The construction circles act as a guide for tangency. Tangency constraints were added to these flat lines to ensure that they're at the correct angles. Lastly, I added these 3-point arcs with the ends attached to the flat lines and the last point attached to the end of the smaller triangle. A tangent mate was automatically added to the smaller construction circle, and the shape I'm left with is a triangle with flat tips and radiused walls. I'll move the rollback bar down a bit and show you a problem I encountered and how I solved it. At this point, I have these 2 features I'd like to pattern: the cuts on the tip and this cut on the side face. If I go into the circular pattern feature I used, you can see that patterning the cuts on the ends worked fine. I can add the features that make up the extruded cut on the side face and the preview appears. But when I click on the green check mark, I get a rebuild error stating that the projection of the sketch on the surface has failed. Even if I were to attempt to pattern these cuts separately, I would still get this error. To overcome this, I used a method that resembles the solution to one of the problems you might encounter on the expert certification exam. That is, because of the cyclical symmetry of the part, I can cut it itself into thirds and pattern that cut body, then combine the result instead of trying to pattern just the feature. First, I used a thin cut extrude with a simple 2-line sketch to cut the part into exactly 1/3. I checked the flip side to cut option to be sure that I'm removing geometry on the correct side of the sketch. Now I can use a circular pattern to pattern the body and rebuild the part. Finally, I'll use combine to make it a single solid part again. Next, I'll show you the housing component and how I created the epitrochoidal shape. After creating the outer and inner edges, I started another unique sketch. This sketch consists of 2 circles of the same diameter, spaced an equal distance from the origin and tangent to the inner edge of the housing. Then I added a 3rd circle of that same diameter and made it tangent to both circles. After using convert entity on this line, I was left with a small pocket in the sketch. This small shaded area is what I used in the boss extrude. Then I mirrored it to the other side, finishing the epitrochoidal shape of the housing. Now that I've shown you these parts, how are they mated together so that the rotary block moves as it should? Here you can see the assembly without the triangular block mated to the rest of the components. In its current state, the center axis of the eccentric shaft is coincidentally mated to a center axis of the rotor housing, and the gear is mated to the eccentric shaft with concentric and coincident mates. Now I can rotate the gear, but I will fix its rotation later. And the only mate on the subassembly as of now is a width mate, centering its location between the walls of the housing. To fully mate the assembly, first I'll add a concentric mate to the inner diameter of the triangular block and the eccentric part of the shaft. You can see that if I rotate the shaft, the triangular block moves with it, but it doesn't spin, so I need to use a gear mate. But before doing that, I need to make sure that the gears are properly positioned. First, I'll set the triangular block in place by using a coincident mate on the right plane of the block and the right plane of the top assembly. This is so I know the block is perfectly centered. Then I'll suppress that same mate I just added. I was just using it to correctly position the block before adding the gear mate. I should also point out that while putting together this subassembly, before adding the additional features to the gear, I made sure to position it with one of its planes centered in the part, so that the top teeth were perfectly positioned. This way, when I mate the top assembly, I can easily match up the teeth of the larger gear and smaller gear, saving me a lot of time. Now I'll do just that by constraining the movement of the smaller gear by adding a coincident mate to its right plane and the right plane of the assembly. All that's left to do is add the gear mate, so I'll click Mate, go to Mechanical Mates, click the Gear option, and I'll select these edges of the gears, typing in the number of teeth for each gear and the pop-up options as I go. Then I'll click the green check mark. Now I can try rotating the shaft. If you don't get the desired result at first, go back into the GearMate options and check the box labeled Reverse. And it works. Now you've seen how to successfully mate a Wankel engine mechanism. But are there any other methods of mating this assembly? What about using a tangent mate or cam mate on the inner surface of the housing to drive the motion? Take the challenge and let us know what you come up with.